Dear colleagues, I would like to acquaint you with some results of our research of fractal properties of various well-known signals. In my report, the basic concepts of self-similar time series and methods of estimating fractal characteristics will be considered. The key points of the proposed generalized approach to estimating will be briefly indicated, and the main attentions will be paid to examples of fractal properties analysis of real well-known signals. A fractal is an object which keeps its structure at scaling. A typical nature fractal is a fern. A very famous geometric fractal is the Sierpinski triangle. Fractal functions keep their structure when the time scale is changed. One of the most famous of these functions is the Weierstrass function. When time scratching or compressing, the Weierstrass function completely reproduces itself, only with a different scale. A random process is called self-similar if at time scaling it keeps the distribution law. The degree of self-similarity is called the Hurst exponent. The most famous self-similar process is Brownian motion. For any compressions and scratches in time, it has a normal distribution law. Only the variance change. Many time series and signals, both natural and artificial, have fractal properties. They include medical signals such as encephalograms and cardiograms. In this case, the fractal analysis helps to clarify the diagnosis. It is known that financial series are fractal, which in crisis change their fractal properties. Self-similarity of telecommunication traffic causes overloads and data losses. Seismic signals also are self-similar, which makes it possible to detect them in the background of natural noise. There are a lot of methods for estimating the Hurst exponent from values of the time series. All of them are based on the fact that in presence of self-similarity, some characteristic of scale has power law dependence of Hurst exponent on time. Let's move to multifractality. A multifractal object is self-similar object which has statistically heterogeneous fractal properties. For example, the right Sierpinski triangle is multifractal. Let's compare self-similarity and multifractality. In the case of random process, self-similar time series are characterized by one parameter, a number, the Hurst exponent. Multifractal time series are characterized by a set of Hurst exponents. A function, this function is called the generalized Hurst exponent. The wider the range of generalized Hurst exponent, the more pronounced its multifractal properties. In the case of monofractality, the generalized Hurst exponent is straight line. Its value is the Hurst exponent. To characterize multifractal properties, Along with the General-Hirst exponent, the multifractal spectrum function is often used. In the case of monofractal properties of time series, the spectrum narrows on one point. The most popular multifractal analysis methods are multifractal dependent fluctuation analysis and wavelet transform modulus maxima. Currently, these methods are implemented in many program languages and mathematical packages. Unfortunately, many researchers use them automatically, which leads to incorrect estimation of the fractal properties of time series. The paper proposed a generalized approach to multifractal analysis. The key points of this approach are the required preliminary estimation of Hirst exponent and the intervals of existence of self-similarity, as well as verification of multifractal properties. Let's move on to examples of using the proposed approach in fractal analysis. This slide shows encephalograms of laboratory animals for different phases of sleep and wakefulness. We see a clear linear dependence, which indicates self-similarity. Our studies have shown that different phases of sleep have, on average, different degrees of self-similarity and different multifractal properties. Slides 13 and 14 present a study of the multifractal properties of cardiograms, namely the so-called RR intervals. It's intervals between the peaks of cardiac activity. At the top, we see the RR intervals for a healthy patient, and at the bottom for the patient with arrhythmia, left before and on right after treatment. The next slide shows the corresponding multifractal spectra. At the top, we can see multifractal spectrum function for a healthy person. At the bottom, the spectra of two patients before and after treatment. We see that after treatment, the spectra of patients shift closer to the spectrum of healthy person. Slides 15 and 16 show the results of study how the multifractal characteristics of encephalograms change when a person performs a physical action and when a person imagines that he is making it. The slide shows the encephalograms of two people who make their first and only imagine it. This slide shows the corresponding multifractal spectra. It's interesting that the spectra of encephalograms for imaginary action are shift to the right for most of the studied cases. On this slide presents the results of multifractal analysis of the blood pressure records of laboratory rats who were on a high and low salt diet. In addition to the fact that the pressure of rats on a high salt diet is higher, the time realizations of pressure have different fractal properties. One of the methods for studying the atmospheric process is analysis of echo signals. We have carried out a study of the fractal properties of such signals. It showed that the echo signals have a fractal properties, and these properties change with the height of the reflecting layer. It's associated with reflections from nearby buildings. One of the known examples of time series with self-similarity properties are seismic waves. Our studies showed that seismic waves have multifractal properties, and different stages of their development have different functions of generalized Hurst exponent. These properties allows to distinguish seismic waves from white noise. This slide shows the results of fractal analysis of indications of ultralight torsion balance that responds to solar activity. We found that they are multifractal, and fractal properties of such time series are different for different seasons. And the last example is the study of the fractal properties of light curves of celestial bodies. Light curves data are taken from the database of National Space Agencies of Ukraine. Studies clearly indicate the presence of fractal and multifractal properties on the light curves for different objects. In conclusion, it should be noted that fractal analysis has become a popular research tool. However, it must be done thoughtfully. Otherwise, you can easily get incorrect results and come to the wrong findings. Thank you for attention.